How can an elevator lift people hundreds of meters without dropping them? How does a wood chipper chew through the toughest branches without jamming? What triggers a petrol pump to stop pumping when your tank is full? To answer these mysteries, we dive deep inside these and other extraordinary machines to reveal the secrets of how things work. The elevator. This time-tested engineering marvel allows us to reach great heights with the push of a button. How does this machine lift people hundreds of meters up and down without dropping them? Tens of thousands of parts work together. At the front, two heavy-duty sliding doors that sense when it's safe to close. Above them, high-tensile steel cables hold the passenger car steady. At the top of the shaft, an electric motor that can lift the weight of a truck. On the side, a lightning-fast emergency brake that can stop a falling cab in a fraction of a second. This motorized metal box has revolutionized our world. The elevator doors must be strong enough to keep passengers safe and stop them from falling into the moving machinery. The key to their strength is the way workers make them in this 60,000 square meter factory in Tennessee.
This is our automated fabrication system.
Keith oversees the machine that builds the doors.
So it goes from raw sheet metal to a finished part without any human touching it. Fully automated. It's really a beautiful thing. I come through and sometimes I'll just stand on the catwalk and watch it run. It sort of has a special place in my heart.
The machine makes each door from a single sheet of steel. First, it cuts the sheet to shape. Then it bends each edge to form a rugged hollow frame. This makes the door both strong and light.
This equipment is capable of producing over 80,000 entrances and doors a year.
The doors may be lightweight, but they still move at speed. So when passengers try to catch the lift at the last minute, how come the closing doors don't crush them? Hidden inside the doors, LEDs create a curtain of infrared beams. Anything passing through them triggers a signal to the door motors. As they start to spin, they drive a rubber belt. The belt pulls the doors back open within a fraction of a second. Thanks to this infrared safety beam, there's no risk of a crush if you cut it fine on the way in. When it's on the move, this 2.5-ton elevator travels at 1 meter per second. It's got to run smoothly. Passengers don't like bumps. To do this, workers must make the machine's pulley wheel just right.
This is one of the parts where our elevator ropes go around it that actually pull up your elevator.
Darryl carefully checks each pulley as soon as it leaves the shop floor. Workers carve these heavy-duty wheels from 50 kilos of solid steel. The pulley's grooves must be perfectly smooth and perfectly round. Anything less and the steel ropes will rattle and give passengers a bumpy ride.
It has to be very precise and very to the 10,000ths of an inch.
Finally, Darrell uses a robotic probe to measure the pulley wheel's vital statistics.
If there were any issues, we would show these fields as red. And this is actually very, very close to perfect cylinder through there, so this is a good part.
The pulley is now ready to give bump-free rides for 20 years or more. This elevator can carry 20 passengers up and down a 30-story vertical shaft. If its speed got out of control, the consequences could be disastrous. So how does the lift catch you if it falls? Safety starts at the top of the shaft. A speed detector has two powerful clamps. If the elevator did start to drop too fast, the clamps bite down. This triggers a lever under the cab, which makes safety brakes slam onto the elevator guide rails to stop a fall if all else fails. Most elevators will never need their emergency brake. But there's another brake that activates every time the elevator stops at a floor. This parking brake clamps on and holds the elevator still as passengers enter and leave.
All of the parameters have been set in the machine, so now I'm getting ready to do a test on it.
James tests the new elevators before they leave the factory floor.
So now I'm running it up to speed, 350 foot per minute. Then slow it back down and make sure the brakes are working also.
The metallic brake pad sits next to the motor at the top of the shaft. It should engage just as the motor comes to a halt. The brake pad only moves a fraction of a millimeter. But once locked into place, the elevator can't go anywhere.
It worked perfectly. The brakes locked on it, so it's a good machine. Now it's ready to go to shipping. Hopefully go to a nice high-rise somewhere in some resort, and I'll be able to ride on it sometime.
This factory builds enough elevators each year to fit a building 8,000 floors high, all flat-packed and ready to assemble on site. It's an everyday machine that performs an incredible feat. Without the elevator, our lives in high-rise cities would be impossible.
Going down.
The petrol pump. Petrol is the lifeblood of our cars, but it's also toxic and highly flammable. So how does the pump fill our tanks without everything going up in flames? More than 2,000 spark-proof parts work together. Carbon blades lift fuel from an underground tank the size of a swimming pool. A vortex chamber removes bubbles from the liquid, while a filter extracts particles. A meter measures the fuel to the milliliter, and a belt-driven vacuum pump sucks out the flammable vapor so the fumes don't ignite, safely filling more than 400 cars a day. But how does this machine always dispense the right amount of fuel and guarantee we get exactly what we pay for? The key to this accuracy is in how the pumps are built in this UK factory. It's the largest operation of its kind in Europe. To measure the fuel, workers install a precision-engineered component called a volume meter.
It's very important that the meter is accurate or the customer will receive the wrong amount of fuel.
Carol and her team build the meters carefully by hand. The pistons must be a tight fit. To give an accurate reading, the meter can't have any leaks.
I'm checking that the seals are not damaged in any way as I'm putting them on. Seals are very important because any damage to them would cause a leak inside the meter and cause the wrong amount of fuel to be dispensed.
Carol ensures the seals on the pistons are undamaged and fits them into the meter body. She then calibrates it to check it is accurate. Inside the pump, the meter goes to work when you fill up your car. As the fuel flows through the meter, it pushes the pistons in and out. This rotates an interlocking set of gears that steps up the speed. The gears drive a magnet mounted on a disc that spins past a sensor. A computer picks up these magnetic pulses and records each rotation. The system counts up the liters with extreme accuracy. So what you see is what you get. The meter is just one of 16 switches and valves inside the finished petrol dispenser. They all need electrical power.
Wiring is a really critical stage because if it's not connected correctly, the dispenser will not work on the forecourt.
Jim makes sure that all the pump parts plug together correctly.
If we do a wrong connection, when the customer picks up a nozzle, it might not work. There might not be any fuel coming through it, or there could be fuel coming through the other side, which is no use to the customer.
Even perfect wiring is still potentially dangerous. Petrol vapor is highly explosive and should never mix with electrics.
If vapours came up from the bottom half of the pump into the top half of the pump, there could be a spark and a catastrophe, a fire at the forecourt.
To make sure this can't happen, Jim passes the wires through a rubber seal.
Because it's a tight fit, it clamps onto the wire and makes it a good seal and stops any vapour.
With the pump's electrical sensors safely connected, Jim's work is done. But the computer doesn't control every sensor inside the pump. It's a mechanical system that stops the pump overfilling your tank. If the pump doesn't shut off when your tank is full, it could flood the forecourt with highly flammable fuel. So how does it know when to stop? The secret lies in the nozzle itself. As petrol fills the tank, air is pushed back up a small channel. The air holds a flexible diaphragm in place. When the tank is full, the fuel blocks the air channel and the diaphragm deflates. This releases a spring that forces a valve shut and cuts off the fuel. This automatic mechanism allows the machine to pump furiously but halt in a split second so it doesn't overflow. This built-in cut-off switch means you'll get a full tank instead of wet feet. Each petrol pump faces a rigorous inspection before it can be installed on the forecourt. Dennis makes sure that each new unit is up to the job. It's critical to check the pumps will dispense the fuel at the right speed.
So you're not taking 10 minutes to fill your car up. It's coming out at a good rate, but then again, it's not coming out too fast so that the petrol will spill all over the place.
The only way to test the flow is to run the pump. But petrol is much too dangerous to use inside the factory.
Petrol is highly flammable. So if for any reason that there's a slight spark, the petrol dispenser would go up in flames and it would cause death.
Dennis uses a liquid called isopar. It flows just like petrol, but won't evaporate or catch fire. Dennis dispenses fuel for exactly 1 minute to test how fast it flows.
As you can see here, the litres are counting up at a steady rate.
He is aiming for a result between 36 and 42 litres.
So our result for that nozzle is 39 litres per minute, which is a good pass.
Just one of 17,000 pumps shipped around the world from this factory each year. More than 3 billion litres of fuel flow through the world's petrol pumps each day. Without this ingenious invention to top up our tanks, the planet would grind to a halt. Air hockey. It has the speed of ice hockey, the skill of table tennis, and the intensity of a boxing match. How does the table keep this puck racing back and forth between players? In the center, a fan with 38 blades sucks in enough air to fill 5,000 party balloons a minute. The air blasts out as high-pressure jets through more than 4,000 holes. Each hole is smaller than a grain of sand. A precisely weighted shatterproof puck is aerodynamically designed to travel at more than 60 kilometers per hour. While hidden microphones trigger sound effects to make this game thrill all the senses. The secret to keeping the puck floating on these tiny jets of air lies in how workers build the air hockey table in this Texas factory. They use more than 25,000 sheets of wood every year. The biggest challenge is to make sure air flows evenly from the fan underneath the table to every one of the 4,000 plus holes in the table's surface. Workers create a complex network of channels inside the tabletop to direct the air.
The machine behind me is now grooving out our play field.
Mike runs the automated machine that cuts these channels. He must make sure every one is the same size and evenly spaced.
The reason we do that is to keep a consistency in the air channels between each channel. So you have a consistent air pressure on every channel.
Workers then glue the playing surface on top. Each row of holes in the surface now perfectly lines up with an air channel underneath.
So you don't have one hole with one amount of pressure, another hole with a different amount of pressure. Having even amount of airflow throughout the system is what keeps that puck floating smoothly and fast.
The perfect air cushion keeps the game flowing. But in the heat of a contest, who will remember to keep the score? Luckily, the air hockey table has an ingenious device that keeps track of who's winning. When a player scores, the puck slams into the letterbox goal at over 60 kilometers per hour. An infrared beam lies in wait. The beam detects the falling puck, and a computer records the point. When the game is over, the computer triggers a magnetic plunger to block the path of the puck. The plunger holds it back until you add another coin. It takes a solid cabinet to hold all this technology together. A finished air hockey table can expect some serious mistreatment over its lifetime.
People will pick the tables up to 3 to 4 feet high and just drop them back down. The tables have to be able to withstand that torture. Kids don't care, it's not their product, so they're gonna be as tough as they can be on it.
Workers carefully build the cabinets by hand to ensure they can withstand this level of abuse. The tabletop weighs almost as much as a baby elephant, so workers attach internal struts to hold it up and keep it perfectly flat.
Wood has a tendency of dipping, swelling, expanding, and these supports will prevent that from happening.
More than 400 screws clamp this turbocharged table together, ready for a lifetime of high adrenaline gaming. Built to last, lightning fast, and powered by air, the air hockey table is a timeless arcade classic. The wood chipper. It reduces garden waste down to a pile of tiny chunks. But how does it munch through tough trunks and piles of leaves without choking? More than 100 parts work together. A 10-horsepower engine as mighty as a motorbike. A compact muffler dulls the whine of the exhaust. A spinning rotor, heavier than a car tire, cuts 120 times a second, slicing solid wood like butter. Steel fan blades shoot the chippings out at 130 kilometers per hour. This merciless machine can shred a tree in minutes. The key to the chipper's chewing power starts life in this family-run metal shop in Wisconsin. They manufacture the rotor plate, the spinning metal disc that holds 2 razor-sharp knife blades.
I'm setting up a 250-ton punch press for the chipper plate.
John has cut and bent metal his whole career. He must use all his experience to correctly set up the punch press. The power of this machine could easily crush a car in seconds.
This here's the chipper plate or rotor plate for the wood chipper. The blades are mounted on the back side here, and this here is where the wood chips would come through once they're chipped up.
The rotor plate spins at the speed of a car engine inside the chipper. It whizzes a blade past the branch 120 times per second. But branches aren't the only green waste that clutters your garden. Leaves cover the ground and stifle your lawn. The chipper's blades alone can't chop through this soft vegetation without getting clogged. The machine needs another weapon in its armory. Behind the blade are 6 ruthless swinging hammers. Driven directly by the crankshaft, the hardened steel pounds the leaves. They have a Y shape for increased surface area and swing to propel the leaves and avoid jams. They deliver a crushing blow 180 times a second. Behind them, fan blades attached to the rotor create a powerful vortex, which shoot the leaves out at 130 kilometers per hour. These flailing hammers spell the end for foliage, but they could also do serious damage to the chipper. The last thing you want is a Y-hammer to come loose when the chipper is at full tilt.
If it wasn't secure, it'd do a lot of damage, flying around and cause a lot of harm.
Jeremy's mission is to make sure the hammers only smash the leaves. The challenge is that the hammers need to be securely fixed, but also be able to swing side to side. Being able to move stops them getting clogged up with leaves.
It's important for them to freely rotate, and we mount them on these pins so they can do that.
Inside the chipper, the forces on the hammers are extreme. Jeremy must create a way to hold them in place so that they can't shake free.
It's going to clamp everything down, and there's no way for the pin or anything to move. But the Y-hammers are still rotating freely.
Jeremy welds the pins between two thick sheets of steel. The metal pieces under the spark get as hot as the surface of the sun and melt together.
The top plate is held securely now after it's been welded, but yet the Y-hammers can still spin freely inside here.
As long as the chipper can keep its hammers and blades spinning, it should be able to crunch through any kind of garden waste. But the task gets more tricky when a thick branch is shoved in. Its success depends on a gadget at the heart of the motor. Ultra-sensitive flyweights spin with the blade. If the blade slows down, the weights fall inwards and pull a lever that reaches around the machine to pull open the throttle. This boosts the power within milliseconds to keep the rotor's blades spinning at the perfect speed. They slice through solid wood without breaking stride. But keeping the rotor stable when it's spinning at 3,600 RPM is a big problem. If it's not securely held in place, this 10-kilogram lump of metal would shake the chipper to pieces. The team on the chipper assembly line has devised a unique way to keep the rotor under control.
When a branch is fed into the wood chipper, it puts a great deal of stress on the machine.
Brian knows the chipper inside out. He's been building these machines for 15 years. To provide maximum support for the rotor, he must connect it directly to the engine shaft underneath. Only an engine with a shaft this thick would be strong enough to hold the weight of the rotor.
The engine has a heavy 1-inch diameter shaft, and it's less prone to breaking or being twisted.
With the rotor in place, Byron builds up the rest of the chipper, ready to do battle in the garden. The ferocious chipping power and insatiable appetite of this machine takes the back-breaking work out of keeping your garden clear. The meat slicer. It slices through every type of cooked meat, one wafer-thin layer after another. How does it cut through the toughest produce to create the perfect slice? Beneath the solid guard sits a razor-sharp blade, thin enough to slice lengthways down a human hair. Driving the machine is a 370-watt motor. A spiked plate grips the meat for ultimate slicing precision. At the top, a boron nitride grinding stone, as hard as diamond, sharpens the blade in just 5 seconds. It keeps this heavyweight machine a cut above the rest. The biggest challenge in the deli is prosciutto. cured for more than a year, it is as dry as leather. The slicer needs a blade that is razor sharp to cut super thin slices of the toughest meats. Workers in this Ohio factory use a special technique to form the blade from a blunt piece of metal.
When the blade starts out, this is what we get into machine. This is our starting point.
Machinist Les is at the sharp end of blade manufacturing. He cuts out specially shaped slots that allow the blade to be mounted on the slicer. The slots must be centered perfectly, or the blade will be useless.
If you don't get this center hole in the center, then it could wear out a motor, it could wear out a shaft. This one looks good.
The blade has an extra layer of metal added to the edge to stop the knife going blunt.
The hard metal on the outside means that you can sharpen the blade very sharp and you can slice the meat very thinly.
Les grinds down the blade to a fine point.
We have to wear special cut-proof gloves because the knife comes off this machine so sharp.
A blade this sharp is essential to carve through tough cured meat. Delicacies like prosciutto need to be cut into layers as thin as paper. How does this machine control the thickness to make the slices so thin you can see right through them? A click of the dial turns a hidden cam gear. Spiraling like a snail's shell, its rotation slides a control arm. This shifts the plate that holds the meat closer to the blade. So you can cut 2-centimeter thick slabs or wafer-thin slices with just the flick of a finger. This precision control and a razor-sharp blade are crucial for cutting the thinnest layers of the toughest meats. But a blade this sharp could be dangerous if left exposed. It's vital that no one accidentally touches it.
If you were to just skim your finger across the blade, it would more than likely leave a pretty deep gash on your finger.
Christian has the job of keeping the slicer safe. He fits a guard around the blade.
The ring guard, it's basically just to protect the operator. It's one of the main key safety features.
He checks the fit using a dummy blade to ensure there is good clearance. With the guard installed, the machine can slice through meat, but is safe for everyone else. The customer demands perfect slices of meat, wafer thin and full length. To achieve a champion cut, the meat must be moved backwards and forwards over the blade in one smooth motion. If it jams halfway, the slice is cut short and is no good. How does the slicer keep the meat moving smoothly? The clamp that holds the meat is bolted to a gliding carriage. This slides along a nickel-plated track. The rail is self-lubricating. Underneath, a sponge pad soaked in oil constantly coats the metal so the carriage can glide fast. At the end of the rail, bumpers absorb the impact so the operator can smoothly slide the meat back and forth. The blade must be razor sharp, or this rapid slicing action will cause the meat to jam on the knife. Workers test every blade before the slicer can leave the factory.
My next job is going to be to make sure that this knife here is very sharp.
Kyle is the man to make sure the blade is up to the task. To test the sharpness, he attaches a plastic flag to the sliding meat tray. The blade must be as sharp as a scalpel or it will simply bend the soft plastic tabs out of the way.
What we want here is for the knife to cut all 3 tabs. And when it cuts all 3 tabs, that lets us know that the knife is sharp all the way around.
Test complete. The blade slices the tabs without bending them at all.
And all 3 tabs are gone, so that's what you want every time before we ship it out.
Finally, the slicer is ready to be shipped. One of hundreds of machines made by this production line each year. With a blade that's never dull and the cutting motion smoother than silk, the meat slicer is the ultimate mechanical butcher. The dentist's drill. Just the sound of it strikes fear into the hearts of many. How does this tiny machine cut through the toughest material in our body? And why does it make that horrible noise? More than 60 miniature components work together. The drill burr is made from tungsten carbide, one of the hardest metals known to man. A driving head spins at 20,000 revs per minute, faster than a Formula One engine. A single gear with microscopic teeth transfers the power. And an air-powered motor with fan blades like a jet engine spins fast enough to create the high-pitched whining sound that people fear. The drill must be tough, but still small enough to use with one hand. The key to this combination is in the way workers construct the drill in this factory in Pennsylvania. The team here specialize in manufacturing precision parts. In a testing lab off the factory floor, they ensure the drill won't restrict the dentist's dexterity.
The last thing the dentist wants is limited movement while drilling. A little yank could end up being damage to the patient's mouth or an injury.
Charles has the solution. The drill is designed with a coupling at the base that allows it to swivel 360 degrees whilst connected to the air hose.
This will help prevent the dentist from missing or accidentally drilling in the wrong area, causing any sort of injury. And just the free movement allows for them to get into much deeper places within the patient's mouth.
The parts that make up the coupling must fit together precisely so they swivel smoothly.
Any deviation could result in poor performance of the drill, air leakage, loss of torque, loss of speed.
So Charles uses an automated measuring machine to check a sample from every batch of completed parts.
This machine will tell us exactly how precise we are manufacturing this component, and if we need to make any adjustments, we could do it on the fly.
This machine measures distances 20 times smaller than the width of a human hair.
If I were to try to measure these dimensions on my own, the old-fashioned way, it would take a long time. Without this machine, we cannot make this part as accurately as we do. All the results came up with green, the part's good, we're gonna keep it running.
Tooth enamel is as hard as rock. To cut through it, the dentist's drill needs to spin faster than the engine in a fighter jet. How can it generate these speeds using just air? As the high-pressure air blasts into the drill, it hits the rotary vane blades. These smooth carbon fiber windmill arms slide over the walls with almost zero friction as they rotate over 300 times a second. A set of minute ball bearings wrap around the shaft to ensure it spins smoothly for a lifetime. The motor must be extremely compact to make the drill small and light enough to use with one hand.
This is the heart of the handpiece.
Griselda is the most experienced assembler in the factory. She needs a steady hand to make the tiny motors.
Putting these springs into the motor, it's the most difficult part.
These springs hold the fan blades of the motor in place. Each one is smaller than a grain of rice. Even with tweezers, Griselda struggles to pick them up.
I get them by the end. Yeah, if I pick them up by the middle, they fly away.
The springs are so small, it takes a trained eye to see if they have been fitted correctly.
We need 5 in each handpiece, in each motor. So if we don't put one and we miss one, the motor is not going to turn.
To finish the motor, she fits these 5 fan blades and a cover to keep everything together.
And this is a complete motor.
The sound may send shivers down your spine, but this powerful package of technology is exactly what you need in your dentist's hand next time you need a filling. The mighty wood chipper, the meat slicer, the elevator, and the dentist's drill. What's inside isn't always big, but it is clever. Next time you see one of these machines, remember, there's more to how things work than meets the eye.